Don't ask, man. Don't ask me what's happening. It's like one of those days where nothing can possibly go right. Everything is going wrong. I'm having difficulties with, I don't know if it's internet or is it hardware issues. Are you guys able to hear me? All right. All right. So I'm not sure if you guys are already registered with, registered with us or not. But if you are, if you're already, if you're already registered with Eptitude, then please log into your online accounts. That's at online.aptitude.co.in. Just visit this URL and log in. And once you log in, look for a link that says class exercise, right? And you'll find today's exercise right there. Yeah, can you guys do this? Just visit the mentioned URL, right? Log into your accounts and access today's session, right? It should be available over there. After all the confusion, the people are joining us now. Yeah. If you guys are here, please let me know in the chat if you guys are around and if you can hear me. Hi. Right. Okay. So, did you guys manage to track the exercise down, class exercise down? Those of you who are attending this class for the first time, you might want to call us, call our office number. This is 9717795955 and ask for Surbhi ma'am. Surbhi ma'am will make sure that you get the class exercise. Great. If you already have the exercise, that's great. Those of you who already are registered students can access this in your testing accounts, online.aptitude.co.in. You log in, look for, in the left panel, look for a button that says class exercise and open that up, right? Download that exercise. That's what it is. Okay, great. So time to, I guess it's time to start today's, kickstart today's exercise. Just give me a second. I'm going to pull that up as well. Yeah. So today's session is on logarithms, right? I know some of you have already, we've already discussed logarithms in one of our earlier sessions, but I thought today would be a good time to quickly recap and understand what logarithms are all about. Right? So what is the logarithmic function? Y is equal to log of x in the base a. What exactly does this mean? Right? So remember that if this is the logarithmic function, if this stands for log, then the opposite of log would be the anti-log. Right? This is the key to understanding the logarithmic function is to understand the anti-logarithm. So what is anti-log? Is if I take the same expression and I write this as x, or let me rewrite this as a raised to the power y is equal to x. Right? This is called anti-log. So what do I infer from here? What is a logarithm? So a logarithm, if I take care of the anti-log, then if x is equal to a to the power 5, then the log of x will be equal to y. The log of x in the base a will be equal to y. What the logarithm says, right? What the logarithm says is what power of the base, let's call it a, makes the radical. That is the question that the logarithm answers, right? What power of a makes x, and whatever that value is what y will return. Let's take an example. So if I say what is log of 16 in the base 2, so you'll ask yourself the same question: what power of 2 makes 16? And immediately you'll get the answer as, okay, fourth power, right? Or if I ask you what power of 3 makes 27, so you'll say, okay, what power of 3 makes 27? This is going to be the third power, because 3 cube is 27. Similarly here, because 2 raised to the power 4 is equal to 16. In fact, I could probably make this a little more interesting by asking you, okay, what about log of 0.001 in the base 10? Right? What power of 10 makes 0.001? So to understand this, you'll have to write the radicand differently. You'll have to say, now the radicand, or x in this case, is nothing but 1 by 1000. Right? So what power of 10 becomes equal to 1 upon 1000? Okay, you scratch your heads a little deeper and you'll immediately realize that since 10 raised to the power a negative number will make the reciprocal. So you want 10 raised to the power negative of 3, because then that will give me 1 upon 10 cube, that's 1 upon 1000, which is exactly what we want. So what power of 10 makes 1 by 1000? The answer is going to be minus 3. Right? So this is the basic concept of a logarithm. What does logarithm do? It asks, when you're using the logarithmic function, to understand the logarithm, you'll interpret it as the y, or the logarithm value, will be what power of the base results in its radicand. What power of a, the base, results in the radicand x. That's what the logarithmic function returns. Is that clear to everybody? All of you listening in, joining us just about now. Some of you are just about joining us now, but I hope this makes sense to you. What is the logarithmic function? This is the main question you want to ask yourself, right? What power of the base a results in x? What power of a results in x? Hence, what power of 2 results in 16? 2 raised to the power 4 results in 16. So what power of 2? Fourth power of 2. Similarly, what power of the base 3 results in 27? Since 3 cube is 27, then this logarithm should be equal to 3. Right? We took a further example. What power of 10 makes 0.001? 0.001 is 1 by 1000, which is also equal to 10 to the power minus 3. So 10 raised to the power the negative 3, 10 raised to the power minus 3 is what results in, what is the value of this logarithm. Right? So that's the basic definition of a logarithm, right? Now, those of you thinking, why am I studying this? Why is this useful at all in daily life, right? Well, one of the most common scales that all of us use. In fact, that the world over gets used very often is something called the Richter scale. I'm sure all of you have heard of the Richter scale. What does the Richter scale measure? What does the Richter scale measure? Yeah. So the Richter scale measures the magnitude of an earthquake. It measures the magnitude of an earthquake. It tells you how severe was the earthquake, right? So how does it do so? Well, the Richter scale is a logarithmic scale. Remember that. Next time somebody asks you to interpret the Richter scale, you should know. You should know that it's a logarithmic scale, which means that whatever the magnitude is that the Richter scale measures, what kind of, recently there was an earthquake in Delhi. Yeah, there was a lot of news about an earthquake happening in Delhi, Delhi being very, very close to the epicenter, which is, I think, around Afghanistan. But Delhi did feel the tremors, right? Now, I think this earthquake was a mild one with a magnitude of around 4.5, right? But, why is it, how does it affect my understanding of the Richter scale? Imagine this, right? So, if the magnitude is 4 versus magnitude of 6 on the Richter scale. Supposing we're talking about the Richter scale, which I know is which I've now told you is the logarithmic scale. Now imagine that you're comparing a magnitude 4 earthquake with a magnitude 6 earthquake. What does this mean? This means 4 will be equal to logarithm of the magnitude. Right? Usually when the logarithm is not mentioned, then you assume the logarithm to be 10, right? So if the Richter scale works on a logarithm of 10, on a base of 10, what is the actual magnitude? What power of 10 makes m? The fourth power, which means m, the actual magnitude should be 10 raised to the power 4. Or in this case, I mean, when we said that the earthquake had a magnitude of 4.5, we say 10 raised to the power 4.5. Whereas m2 will have, if I use the same logic, m2 log of, right? So this is okay. Earthquake 2. This is earthquake 1 and this is earthquake 2, right? So if 6 is the magnitude as measured on the Richter scale, right? This should also be equal to the logarithm in base 10, which means what is magnitude 2? What is m2? 10 raised to the power 6. So while the Richter scale seems to say 4.5 to 6. I mean, it doesn't seem too very severe, right? How much of a difference is 6 as compared to 4? Not much. But if you now consider the actual magnitude, not on the Richter scale, but the actual magnitude, then what do I have? 10 raised to the power 4 is the magnitude of the first earthquake. That's like 10,000. Whereas the second magnitude is 10 raised to the power 6. That's like 1,000,000. Can you see this earthquake is 100 times as severe as M1, the previous earthquake, right? So when the Richter scale moves from a magnitude of 4 to 5, it becomes 10 times as severe, right? If it goes from 4 to 6, it becomes 100 times as severe. If it goes from 4 to 7, it becomes 1,000 times as severe, right? Don't even try to imagine what happens if it goes to 8, right? If an earthquake of magnitude 8 hits any of our civilized cities, rampant destruction, right? Probably cities will get flattened out in entirety. Yeah, which is why you don't hear about them too often. Most of these severe intensity or severe magnitude earthquakes are usually underwater, right? Anyhow, so not a science lesson, but I hope it makes sense, right? The logarithmic scale, right? The logarithmic scale basically only measures, the magnitude of a particular quantity, but as a logarithm, not in absolute sense, but as a logarithm. Okay. Now let's open the exercise and try the first few questions. Look at the first one. Right. The first question in today's exercise says, what is the value? Find the value of the given logarithm. This one says find the value of. I'll let you guys respond. Right. Let's try and keep it interactive, guys. I would like you guys to let me know what answer you get to the first question. Do I have any answers yet? Okay, I have one very quick answer. Arushi. All right, very surprising that I'm getting multiple answers still. Right, so what power of? The question is, find the log of value of log 7 in the base 343. So now immediately your question is, if this is equal to y, then taking anti-log, right? Now you should know this operation, right? If an equation is given in logarithm term, you should be able to convert it into anti-log. How? The base raised to the power y should be the radicand. So here I'll say the base taking an anti-log. Taking an anti-log in this case, the base 343 raised to the power y should be equal to 7. And I know 343 is 7 cube. So 7 cube raised to the power y is 7, which means 7 raised to the power 3y is 7 raised to the power 1, which means 3y is 1 or y is equal to 1 by 3. Right? So the answer to the first question is option A. The answer to the first question is option A. Great. A lot of you guys got the answer. Nice. Try the second one. What power? And I'm going to write the log anti-log operation to the right just as a reference for us. Right. So we're going to say, okay, if y is equal to log of x in the base A, then the first operation we learned is the anti-log, which basically says x will be equal to a to the power y. Right? So that's one thing we've learned. So if I use that in the next question. All right? Yeah? What power of the base makes the radicand? This one is, find the value of y is equal to log of 32 in the base square root of 2. There are two ways in which you can think about this. You can either use the logarithm, you can either use the anti-log and remove the log in this, or you can say what power of, use the basic definition, what power of the base root 2 gives 32, which means root 2 to the power of y is 32. So what would the value of b of y be? Now think about this. Root 2 when squared results in 2, and 2 raised to the power of 5. 2 raised to the power of 5 is 32. So root 2 raised to the power, this is like 2 raised to the power half raised to the power y is equal to 2 raised to the power 5, which means 2 raised to the power y by 2 is 2 raised to the power 5. Equating the powers. Equating the powers here. I'll get y by 2 is equal to 5 or y is equal to 10. Fairly straightforward. Yeah. Nice. Try the third one. And then there's plenty of questions in today's exercise. I'll try and quickly sort of run through the majority of them, but at least the ones that should be troubling you. Hardik, to access the class exercise, log into your online account, and that's at online dot. This is where your tests are, and look for class exercise. Okay. I have a quick answer from Anupriya saying, oh, okay, answering the previous question. About question number 3, guys, the logarithm of 0.0625 in the base of 2 is equal to what? Right, so it says the logarithm of 0.0625 in the base of 2 is equal to how much? Right, so, okay. 2 answers so far, -4 and 0.25. You want to be checking your answers, guys. Yeah, let's do the same thing. Let's make it equal to y and take the antilog, right? Antilog would mean this power of the base, which means 2 raised to the power y is equal to the radicand, 0.0625. And if I remove the decimal, this is going to be 625 upon 10,000. Cancelling it out by 25. 25 into 25 is 625. 25 fours are 100, so that's 400. Again, if you divide 25, ones are 25 and 25 sixes are 150. So what you get is 2 raised to the power y is equal to 1 by 16, which is like 2 raised to the power minus 4. So if I take a careful look at this, then the power should be y, which is minus 4. Does that make sense? Thank you, Mr. Driven. I'm not sure what drives you, but your appreciation certainly drives me. So, hope this is working fine for you guys. Yeah. Are we reverting to Victorian English now? Sire and whatnot? Okay, great. Hope this is clear, right? So, first basic problem type in the logarithm is to know how to calculate a logarithm. Is to essentially determine the value of a logarithm. Trick or key to knowing that, to be able to do that, is to understand the antilog operation. Is to be able to take a logarithm and to be able to write it as an exponent, right? So next time next time the logarithm troubles you, remember logs is nothing but exponent. You can completely remove the logarithm and write it as an exponent. Keep that in mind. Okay, do we have anything else from logs? Okay, now I wanna, before we move on to the next few questions, I want to quickly discuss the properties of logarithms. Right? What are the important properties of logs? Right? Okay. Now the first and foremost property is that, right? And what we'll do is I'll try and compare just so that you get a better understanding. Right? We've already established that logarithm is nothing but the exponent when flipped around, right? On a different scale. So all properties of logs will be mirrored by properties in exponents, right? So think about properties of exponents, right? What do you do with exponents? A raised to the power m into a raised to the power n is equal to a raised to the power m plus n, right? So when you multiply two exponents, their powers get added. Similarly, in logs, the properties of logs are that when you add two logarithms, x1 plus log of x2, as long as they have the same base. Remember, in both cases, the bases have to be equal. If you add two logarithms, then this will be equal to log of x1 into x2. It's the same as multiplying their radicands, right? Remember to write this both ways, right? Remember to understand this both ways. Either logarithm of a product will be sum of their logs, individual logs, or the other way around. If you have the sum of two or more logs, then you can actually multiply their individual radicands. Right? So that's the first property. The second property is that if you were to instead subtract log of x1 minus log of x2, both of them in the same base, then instead of multiplying, you divide in the same base. Right? This is mirrored in the property a to the power m divided by a to the power n is equal to a to the power m minus n, right? So while here the powers get subtracted, which results in the exponents getting divided. Similarly here, if logs get subtracted, then their radicands will get divided. You can see that there is almost a one-to-one correspondence in even the properties. Right? Okay. Third similar property is, what if I take a number which has a radicand which has an exponent? What if the logarithm itself contains an exponent? No problem. This power, remember, you can actually derive this property, because what is x to the power n? It is the product of x with itself n times. So you can think of this itself as x into x into x into x. And then if I use the first property, when you are multiplying two things inside the radicand, then their logarithms get added, right? So here I'll end up getting log of x plus log of x plus log of x n number of times. So this will result in n into log of x in the base a. Yeah, so that's the third property of logarithms. Again, mirrored here as if you have a raised to the power m whole raised to the power n, then you end up multiplying their powers. Right? Okay. And the fourth most important property is called the change of base property. Right? And in fact, before I introduce the change of base, here we said, what if the radicand has a power? What instead? The base has a power. Right? So the property here is, if the radicand has a power, then n comes out in the numerator. But if the base has a power of n, then that n will come out in the denominator. Right? Remember, the base has changed from a to the power n to a. So if you are changing the base from a to the power n to a, then that power n has to come out in the denominator. Right? Whereas if you want to change the radicand from x to the power n to x, so if that power of n has to come out, it will come out in the numerator. Right? So it's a fairly easy association. If the radicand has a power, it will come out in the numerator. If the base has a power, it will come out in the denominator. Right? So you can probably keep that in mind. All right. Let's move things ahead. Right? So these were the four basic properties, but there's also a fifth very important property. Right? In fact, the fourth property is derived from this one. Right? This is called the property of change of base. Right? As the name suggests, what I'm going to do here, what I'm attempting to do, is that if I have the base of a logarithm as a, how do I rewrite it with another base? How do I, for example, rewrite it as logarithm in the base of b? Yeah. So if you ever want to change the base to b, here's a quick trick. The change of base formula will include two logarithms, one in the numerator and one in the denominator, both having the base as b. And the numerator will be a logarithm of the earlier radicand. Denominator will be the logarithm of earlier base. So basically, log of x in the base a will be log x by log a, whatever base you want to choose. Right? So log of x in the base a will be log x numerator upon log a in the denominator. And the base is one that I can choose. The base is one that I decide. Yeah. So for example, let's take examples of this. Right? So if I give you log of 2 as 0.3 and log of 3 as 0.45 and ask you, okay, what about log of 6? Right? How do I calculate the value of log of 6 given these two values? You'll say, okay, by observation I can see this is 2 into 3. And then if I use the first property, whenever the radicand has a product, that can expand into the sum of the two logarithms. So this will be log 2 plus log 3. And so I can substitute those values and I'll get 0.3 plus 0.45 gives me 0.75. So the value of log 6 is 0.75. Right? Similarly, if I ask you what about the value of log 1.5? So to calculate the value of log 1.5, you'll say, okay, this is log of 3 by 2. What is 1.5? 15 by 10. 15 by 10 simplifies into 3 upon 2. Now I have a log containing a division. So if I have a log containing a division, then I can rewrite this as the difference of two logs. So this can be written as log of 3 minus log of 2. And take the two values. Log of 3 is 0.45. Log of 2 is 0.3. So I end up getting 0.15. Right? So the log of 1.5 is actually 0.15. It's a very fortuitous thing, right? It doesn't usually work out this way. But then, given these values, this at least is true. Yeah. Similarly, if I ask you what is the value of log 16, so remember you already have log of 2. So if I write this as log of 2 raised to the power 4, then by using this property, whenever the radicand has a power n, that power n comes out in the numerator. So I'll write this as 4 log 2, and log 2 is already known as 0.3, so this becomes 4 into 0.3, that's 1.2. Right? So the very quick illustration of how I can use the various properties of logarithms. Right? How They can help me evaluate a variety of simple problems, right? Simple problems that involve logarithms. Yeah? Hope this is clear. I hope this is making sense to you guys. I've given you the properties here. For the first three properties, I've given you illustrations. This is the first illustration, second illustration, and third illustration, right? So, for the first three properties. Let me move on. Let me actually give you an illustration for change of base. Supposing I ask you, what is the value of log of 64 in the base 32? Yeah. So what you could do here is, if you use the basic property of basic definition of a logarithm, what does it say? What power of 32 makes 64? It's a weird question to ask, right? Because the first power of 32 is 32 itself. The second power of 32 is going to be a very large number. In fact, those of you who know it will know it as 1024. So very, very large number. So no way that any of you remember what power of 32 makes 64. But what you can notice is that the base is nothing but a power of 2, and in fact the radicand also is a power of 2. So I can use a mix of properties 3 and 4. I can combine these properties 3 and property 4. What does property 3 say? Whenever you have x raised to the power n, I can take the n outside and write as log x. So I can bring the 6 outside, and then this will become log of 2. But similarly, if the base has a power of n, that n will come out in the denominator. So I can bring the 5 out in the denominator and leave this as log 2 in the base 2. So what power of 2 makes 2? Okay, this is an easy one, right? What power of 2 makes 2? First power. So this becomes 6 by 5 into 1, that's 6 upon 5. Yeah, it's fairly straightforward. So that's your answer, 6 upon 5. Right? That's the value of log of 64 in the base of 32. In fact, the 6 by 5th power of 32, a little more than 1. 6 by 5 is 1.2. So 32 raised to the power 1.2 actually results in 64. But it's not something that you would be able to guess. Okay, so those are your basic properties. I mean, there are a few more properties, but let me reserve those for later, right? For now, I'd rather you get comfortable with the basics, right? Understanding how logarithm works in general and know how to apply it on a variety of simple basic level problems. Okay, let's come back to the exercise for today, right? Okay, try question number 5. Log of P is given to me and log of Q is given to me. Then how do I equate P and Q? See if you guys are able to figure out question number 5. For a while, I'm going to leave the properties on the board. Alright. Couple of really fast, quick answers, which is great. Log of P is equal to 25, log of Q is equal to 5, right? Notice that the bases are 8 and 2. So log of P in the base 8 is 25, which immediately means taking an anti-log. If you take an anti-log, then base raised to the power 25. So 8 raised to the power 25 is equal to P. Similarly, the other equation is log of Q in the base 2 is 5, which means if I take an anti-log, then 2 raised to the power 5 is Q. Clearly I can rewrite this because 8 itself is a power of 2. So bring that down and write this as 8 as 2 Q. The power of 25 is P. When an exponent is raised to another power, powers get multiplied. So this becomes 2 raised to the power 75, which is P. But if I want to equate this with vis-a-vis Q, then I can write 2 raised to the power 75 as 2 raised to the power 5 into 15. And what is 2 raised to the power 5? I can then write this as 2 raised to the power 5 whole to the power of 15. If this is P, substitute the value of Q from there. to the power 15 is equal to P. So there's your answer. P will be equal to Q raised to the power of 15. That's option A. Right. Let's move things ahead. Discuss the next one. Question number. Try question number 6. Give you guys a minute. Try question number 6. We're given the value of log y in the base x and log x in the base 2. See if a combination of antilogs gives you the answer. Okay, I'm getting a mix of mixed bag. Yeah, most of you are saying option C. Yeah, let's see. Let's check this out. So, what do we have? Given log of y in the base of x is 100, and so if I take an antilog here, this will result in x raised to the power 100 is y. Leave it at that. The second equation given to us is log of x in the base 2 is equal to 10. Right? So if I take an antilog here, this will convert into 2 raised to the power 10 is equal to x. Let's take this and substitute it above. 2 raised to the power 10 raised to the power of 100 is equal to y, which means y is 2 to the power 1000. Right? Is that what the question asks? Yes, indeed. The question says find the value of y. The value of y will be 2 to the power 1000, which is actually option C. Does that make sense to you guys? It won't be 2 raised to the power 100, it will be 2 raised to the power 100 into 10. That's 1000, that's option C. Yeah. Okay, on to question number 7. Try the next one. And it looks like one of those questions which intimidates more than needed. All right. What is the value of x? Right, it's a question that's entirely dependent on your ability to take an antilog. Right. So here's how you read this question: log in the base 2 of another log in the base 3 of another log in the base 2 of x. This is given to me as equal to 1. Right? So you start taking antilog from the outermost log. So if log of something is 1, then the value inside the radicand log 3 of log x will be equal to 2 raised to the power 1. So you use the power along on the base of 2. So 2 to the power 1. Next up, you'll say 3 raised to the power 2. So 3 square will be the value of the radicand, log of x in the base 2. So this is 9. Next up, 2 raised to the power 9. 2 raised to the power 9 will be the radical x. What do I get? X is 2 to the power 9, which is 507. Right? Very easy question. Yeah? It's a series of antilogs. Right? It looks intimidating, no? It looks scary. Log of log of log. Yeah? No big deal. It's like if I were to say 2 raised to the power x raised to the power y raised to the power z. I mean, it's not really as scary, right? Because what this means is 2 raised to the power x into y into z. Right? Similarly, log of log is quite an easy thing to calculate because you know that starting from the outermost log, you will continue to take antilogs. Is that clear to everybody? The answer to question number 7 is option D. Is that clear to all? All right. Right. So again, we're still at the shallow end of the stream. We're still doing some easy questions. We'll come to some harder problems, right? But at least do some practice first. Right. Try question number 8. I want you guys to try question number 8. We have an expression that says log of 26 by 51 in the base 10 plus log of 119 by 91 again in the base of 10, right? And then there is a negative sign minus log of 13 by 32 in the base of 10, and finally I have another negative log of 10, 64 by 39, right? So if I use combination of property 1 and 2, whenever things get added, you should multiply their radicals. Whenever things get subtracted, divide. So here there are 4 things, and right, so these two are getting added. I'll multiply their radicals. 26 by 51 into 119 by 91, and then these two get subtracted, which means they should be divided. Their radicals should get divided. When you get divided, it's like the multiplication of their inverse. So let's invert the radical. 13 by 32 becomes 32 by 13. That gets multiplied. Similarly, this will also get inverted. 39 by 64. Right? And you can immediately see that this calculation is quite simple. 13 3s are 39. And then 13 2s are 26. 13 7s are 91. Right? 17 3s are 51. 17 7s are 119. 7 and 7 goes away. 2 and 2 goes away. 3 and 3 goes away. We're left with 1. So that becomes log of 1 in the base 10. Now ask yourself, what power of 10 makes 1? What power of 10 results in 1? 10 raised to the power 0. Right? Why? Because 10 raised to the power 0 is 1. So what power of 10 makes 1? The 0th power. So my answer to question number 11 is option A, 0. Very nice, very nice. Some of you got this fairly early. Right? Okay, now that you understood these basic ones, right, I want you to try question number 10. Right? It's a question that still uses the same basic property but uses it as a sequence. See if you're able to figure it out. Question number 10. Have any answers yet? Okay, somebody's talking about the NPAT mock. Absolutely, trigonometry is never easy. Trigonometry is always a little obtuse, isn't it? I'm not surprised. Mr. Driven, I think you want to tell us what your good name is. Okay, I have 2 answers so far. 3 rather. Arishi, I think you want to check your answer. See if you're reporting the right value. Are you reporting the logarithm or are you reporting the radical? Oh, okay, Christian. Yeah, Christian. So what I mean, we're gonna do trigonometry, right? We've already done trigo once. We'll do it again. Give you some additional problems. I'm not sure how it affects, how taking an online test helps with that. But trigonometry is something you're gonna have to really, really work hard at. All right. So back to this question. So I have log of 1 by 2. Right? And then it's plus log 1 by 3 plus log, and I can see the pattern, right? It's going to be 1 by 3, then 1 by 4, then 1 by 5, right? And it says go on to 198 terms, right? So the first challenge for me in such a question is to write the last term. What will its value be, right? Now, I don't know about you guys, but I don't like remembering formulae, right? I know you can do this by using the formula for an AP, right? I don't like that, right? Easier thing to do is to use a common sense. Use your common sense. How do I do that here, right? Think about it. You want the 198th term, right? Because this sequence has 198 terms. You want the 198th term. So go back, rewind karo usi ko, right? If I want the 190th term, what about the first term? So go back expression and say, okay, the first term has denominator as 2 because the numerator and the mixed fraction contains 1 in the integer part and 1 in the numerator. In fact, all numerators and all integer parts are the same, right? So the only thing is the denominator. So for the first term, denominator is 2. For the second term, denominator is 3. Third term, denominator is 4. What do I see? What is the pattern? Whichever term you want, add 1 to it and put that in the denominator, right? So second term becomes 3. Third term becomes 4. So 198th term would make it 199 in the denominator. So 1 by 199, right? So that's the first inference. I can then generate the last term, the 198th term. Okay. The second thing, I'll use property 1, right? Because I'm adding a lot of logs. I'm adding 198 terms. So the moment I add 198 terms, I can multiply their 198 radicals. So, but before I multiply, I should convert them all into normal fractions instead of mixed fractions. So let me rewrite them. 1 by 2, 2 into 1 2, 2 plus 1 3. So this becomes 3 by 2. Multiply this with the next radical, that's 3 plus 1 4, 4 by 3. This one is 5 by 4. And now I can see the pattern, right? 5 by 4, 6 by 5, all the way till 199 by 198. And then for the last term, it's going to be 200 upon 199. Right? So here's what I get. And then you can see 3, 3, 4, 4, 5, 5, 6, 6, all the way till 199. Everything gets cancelled. So what do I get? I get log of 200 upon 2, which is log 100. Right? And remember, whenever the base of a logarithm is not given, in fact it is given here, but even if it weren't, whenever the base is not mentioned, you will treat the base as 10. So this is log of 100 in the base 10. What power of 10 makes 100? The second power. Right? What power of 10 makes 100? The second power. So 10 square is 100. That gives you the final answer as 2. Right? Yeah, fair enough. What looks so hard isn't hard, right? Actually, all of these questions should be done under 1 minute. Shouldn't take you more than a minute. Okay, that's great. Now I want you to try question 12. Question number 12. Everybody try question number 12. Okay, Anshuman, point taken. I will discuss that one too. Okay, it seems to be troubling most of you. Quite unusual. On the face of it, looks like a innocuous little problem, right? I'm given that log of AB when the base is A is equal to X. So I'll expand this. I'll write this as log of a product and use the property in reverse will be log of A plus log of B. Both of them being in the same base originally. A. So what power of A makes A? What first power? So 1 plus log of B in the base A, right? And here I can use the change of base. I can write this as log B by log A. What am I doing? I'm changing the base to 10 is equal to X, which means I get the value of log B by log A. When I don't write the base, it means it is 10. This is X minus 1. So I have this relationship, have this equation, right? Move on to what is the question asking me? Find the value of log AB in the base of B. Which means again, if I calculate, I split this using the first property. Log of AB would be equal to log of A plus log of B. So log A in the base B plus log B in the base B. It's very obvious to see second term would be 1. B raised to the power. What power of the base B makes the radicand B? So what power of B makes B? First power. So 1 plus. And here I'm going to apply change of base. I'm going to write this as log A upon log B. Both of them in the base 10. So if I want to use this relationship, I know that this is the inverse of that, which means this will become 1 upon this x minus 1 plus 1. So I'll get 1 plus x minus 1 over x minus 1, which means I get x upon x minus 1. That's option D. Yeah, fairly obvious, right? Not at all as hard as it seems. Okay, some of you wanted me to discuss question number 11. I shall oblige. Find the value of the given expression. And the value of the given expression. What do I have? Log 2 plus 16 log 16 by 15 in the base of 10. And plus 12 log 25 by 24. And plus 7 log 81 by 80. All of them with base 10. Okay, I'll give you a minute to think about this. Okay, here's a hint. Right. So clearly, if I have the sums, ideally I'd like to multiply their radicals. The problem is that they have coefficients also. No? So what I can do is I can use property number 3. I can say whenever something a log has a coefficient, you can take that coefficient inside by raising the exponent to that base. Yeah. So here this will become log 2 plus log 16 by 15 raised to the power 16 plus log 25 by 24 raised to the power 12 and log 81 by 80 to the power of 7, and that then I can multiply these. So this becomes log 2 into, now obviously when I multiply, I'm going to write 16 as 2 power 4 raised to the power 16 upon 15 can be written as 3 into 5, so 3 power 16 into 5 power 16. Here similarly I have 25, which is 5 square to the power of 12 upon 24. 24 is 3 into 8, so 3 into 2 cube whole power of 12 into, sorry, all of these are getting multiplied. 81 is 3 power 4 to the power 7 and 80 is 16 into 5, so that's 2 power 4 into 5 whole raised to the power of 7. So then, yeah, it's a question that began as a logarithm but became one of exponents, right? So now use the property of exponents. First one, power get multiplied. So 2 to the power 4 into 16, 64. This is 3 power 16 into 5 power 16. Here I have powers multiplied, 5 power 24 divided by 3 power 12 into 2 power 36 into 3 power 7 fours are 28 upon 7 fours are 28. 2 power 28 into 5 power 7. So you can see that all of these terms contains 2's, 3's and 5's. So let me combine all the 2's. Wherever the powers are getting multiplied, add the powers. Wherever they're getting divided, subtract. So in the numerator I have 1 plus 64 minus 36 minus 28. Then I have 3 raised to the power, numerator is 28 minus denominator is 16, denominator is 12, and that's it. And 5 raised to the power 24 minus 5 power 16 minus 5 power 7. Right? So if I rewrite this, what do I get? Log of, this is 50, 64 actually. 64 less 64, this will actually get cancelled out. So 2 power 1, 2. 16 plus 12 is 28, so this goes away. 3 power 0 is 1. And this is 16 plus 7, 23. 24 minus 23 is 1. So this becomes 5. So what do I get? Log of 10 in the base, 10. What power of 10 makes 10? Obviously the first power. So my answer is going to be 1. Is that clear to all? Specifically, this question, right? It looks like a very intimidating question because of the coefficients. But I mean, the idea is to first apply property number 3, and then apply property number 1. So property number 3 takes the powers inside, and then property number 1 multiplies all of these radicals. And then once you have product of radicals, which are all exponents, you can rearrange them by using the property of exponents. Is that clear to all? Right. Enough, I think. By now you should be used to the various properties of logarithms, right? Certainly, hope that is so. Right. Okay. So do a few more variations and then we'll go on to some harder problems, right? Okay, try question number 16. I want you guys to try question number 16. Okay. Right. So, okay, I have one person saying B, another saying D. Seems to be some confusion on this one. So, I mean, here's how I think about this question, right? And log of 27 in the base 12 is given to me as A, and the question says find the value of log of 16 in the base 6, right? So you'll obviously look at first of all base. Here the base is 6, here the base is 12. Not really a power of 6. Right? Similarly, this is a radicand of 27, that's a radical of 16, right? So seemingly there is no relationship between the two, right? But what are the prime factors of 27? 3 cube. 12 is 2 into 2 square into 3 rather. 4 into 3 is 12, right? So basically here the radicand and the base are both numbers that contain 2 and 3 as prime factors. Here also the radicand is a power of 2 and the base is a power of 2 and 3. So that's the hint, right? That when I work with this, I'll change the base, right? So apply change of base, right? I can change it to any suitable value, but let's choose 10. So we'll write log 27 upon log 12 is equal to A. But if you write 27 as 3 cube and you write 12 as 2 square into 3, then the value of A becomes, take the using property number 3. When you have radicand containing a power, it comes out, right? So log of this becomes 3 log 3, and this becomes, first of all, you have a product, so the logs will get added, and then the first logarithm will have log 2 square. So that power will come out. So I get 3 log 3 upon 2 log 2 plus log 3 is equal to A. Right? So I get an equation like this. Right? Now clearly this equation is not very convenient. I mean, incidentally, if you don't know how to work with this, then you can stop here. But and then understand from here what will I need to do with this expression, right? So let's come back here and we'll say, okay, this is log of 2 power 4 in the base of 6. So if I apply change of base here, let's say this is x, you want the value of x. X will be log of, so change of base, log of 2 power 4 divided by log of 6, which is 4 log 2 divided by log 6, which is log 2. 6 can be written as 2 into 3, right? So log 2 plus log 3. And now you can see that, well, I want to use this. It doesn't seem to be that easy. So how do I do this? Basically what you do is, both of them contain, remember, numerator contains log 3, denominator contains log 2 and log 3. So if you divide numerator and denominator by log 3, what do I get? We'll get basically from here. So dividing by log 3, numerator becomes 3. Right? Log 3 by log 3 will become 3. And that log 3, if you divide the denominator by log 3, you get 2 times log 2 by log 3 plus log 3 by log 3 will be 1. This should be equal to A. Right? So if I consider this value as, let's say, t, so I get 3 upon 2t plus 1 is equal to A. So can I calculate the value of t? So if you inverse these, if you exchange these, you'll get 3 by A will then be equal to 2t plus 1. So the value of t will then be 3 upon A minus 1 divided by 2. You take this value of t and you substitute it here, right? But to do that, first you'll have to create t. First you'll have to create t. What was t? T was log 2 upon log 3. So to create log 2 upon log 3 here, even here you divide by log of 3. So which means x becomes equal to 4 into log 2 by log 3 upon log 2 by log 3 plus 1. And then you substitute the value of t, which was equal to log 2 by log 3. You substitute the value of t, and then this will become 4 times log 2 by log 3, 4 times 3 upon a minus 1 into half divided by half of 3 upon a minus 1 plus 1. And you simplify this. It should give you the answer, right? So if I quickly check, right? So numerator will come 2 times. I've run out of space, so I'm going to do this, right? To do this remainder here. So this becomes 2 times 3 minus a upon a whole divided by, take an LCM, this will become half of 3 minus a plus 2a rather, whole divided by a and a will get cancelled out. This 2 will go into the numerator. This will become 4 times 3 minus a upon 3 plus a. 4 times 3 minus a upon 3 plus a is option D. Yeah, does that make sense? देखो मतलब, I mean, this question involved a lot of workings, but the concept is I can change the base, write it in terms of log 2 and log 3. Sure, also I can write this in terms of log 2 and log 3, and somewhere I'll have to use a ratio from here and utilize it in the other equation, right? So in a gist, if you want to capture this in your memory as a question type, then you know that, okay, here's a question where I use a ratio or I calculate a fraction here and substitute the value of that fraction in the second equation. Okay. A lot of logarithms also get featured in sequence kind of problems, right? Like for example, okay, try question number 18th. Try question number 18th. From the exercise set, question number 18. Find the value of the given expression that contains a reciprocal of 3 logs. Right? Alright, so here I have 1 by log 16 the base 3 plus 1 by log 16 the base 4 and 1 by log 5. It's a very easy question. I can see that the bases are different. I want to convert them to same base. Change the base. Apply, change the base, right? Then this can be written as log 60 by log 3 and log 3 will go in the numerator. So this will become log 3 by log 60 plus log 4 by log 60 plus log 5 by log 60, and the log 60 obviously is an LCM, is common, which means you'll end up getting sum of the 3 logs, and when you have sum of 3 logs, it will become log of 3 into 4 into 5. It turns out 12 into 5 is 16, so log 60 by log 60 will become 1. Yeah, so answer to this question is option B. Okay. Right. Okay, try 22. Question 22. I'm glad, Sanjana, you find that easy. Question 22. If log x minus 5 log 3 is equal to minus 2, then what's the value of x? So our first step I'll do is write this as log x, take the power inside, minus log of 3 to the power 5 is equal to minus 2. When two logs are subtracted, then using the property it will be log of a upon b. So x upon 3 power 5 is equal to minus 2, which basically means in the base is not mentioned, it's 10. Right? So taking an anti-log, base raised to the power minus 2 would be equal to the radical. So x upon 3 power 5. 3 power 5 is 243 is equal to 10 to the power minus 2, which is 1 by 100. So what is the value of x? 2.43. 243 upon 100, which is 2.43. Good, good. A lot of you guys managed to figure this out. Okay. Okay, more on the same lines. Okay, how about question number 25? How about question number 25? Value of log 2 is given, and the question asks you to calculate the value of log 5. If log 2 is known, what is the value of log 5? Okay, at least some of you remember what we did this, how we dealt with this in class. Right, so if log of 2 is 0.3010, how do I calculate log of 5? Right, and both of them are in the base 10. Let's say this is x. Right, so clearly what I want to do is I want to use these two, right, in conjunction. So what I do is add. So log 2 plus log 5 will be x plus 0.3010. But when two logs are added there, radicands will get multiplied. So 2 into 5 is 10. And the base is also 10. So what power of 10 makes 10? First power. So this should be x plus 0.3010, which means that the value of x will be 1 minus 0.3010, that's 0.69. That's option C. Very nice. Yeah. Okay, just for courtesy's sake, let's try one more question. 27. See if you guys can apply. Try question number 27. Okay, so easy one. Yes, thank you for underlining it as a very easy question. I know it was, right? We did solve this before, right? So log 1.5 will be log 3 upon 2, which means log 3 minus log 2. So just subtract the 2. Answer is 0.1761. In fact, the calculation is also very easy because option choices are all very wrong. All option B, C, and D can't be the difference, has to be option A. Right? Another variation of this, another kind of question from logarithms, involving logarithms, is question 28. One that talks about number of digits in a number. Right? Look at this, question number 28. It's quite a popular question, involving logarithms. It basically says that if log of 2 is known as 0.30103, right? If the value of logarithm of 2 is known, then how many digits are there? And the number of digits in 2 raised to the power 64. So that's the question. So what I do is I start with the value of n. The big hint I have is that we're doing this with, and the question also gives me a log, so I know what to do next, right? Immediately I know that I should take log. Taking log on both sides, log of n would be equal to log of 2 to the power 64, and I know that the power will come out, so this becomes 64 times log 2. And using the value of log 2 already given to us, this will become 64 times 0.30103. Right? So let me quickly multiply. 64 into 3 is 192. So 92 and 1. 64 ones are 64 plus 165. And again 64 into 3 is 190. So what I get is 19.26592. This is what I get. 19.26592. This is the value of log of n. Right? Now, unfortunately, I didn't want the value of log of n. What I wanted was the number of digits in n. So, since you want the number of digits in n, let me take the anti-log here. Take anti-log. The moment I take anti-log, this raised to the power value equal to the radicand. So, n would be equal to 10 to the power 19.26592. Now, whenever in such a problem, whenever the power of 10 is 19 point something, you know that the number of digits will be one more than the integer side, integer value. The number of digits will be 20. That's your answer, right? But those of you questioning why that is so, right? And obviously curiosity and questioning is important, right? So why does that happen, right? So just take a look. I have n as 10 to the power 19 point, what was this? 2659. I can write this as 10 power 0.26592 plus 19. 19.26 can be written as 0.9.26 plus 19. And when you have a power m plus n, I can split this as a power m into a power m. This splits into two parts. Now, focus on this part. Right? Now, you know that 0.26592 in terms of value lies between 0 and 1. So, when all three numbers are used as powers, then 10 to the power 0 will be the least, 10 to the power 1 will be the highest, and 10 to the power 0.26592 will lie somewhere in the middle. Right? Remember, this is so because the base is greater than 1. Right? This relevance of this will become clearer. So since the power lies between 0 and 1, 10 to the power of 0 and 10 to the power 1, basically same ascending order will exist for even their exponents. So what I end up getting is 10 to the power 0.26592 lies between 10 power 0 which is 1 and 10 power 1 which is 10. Since its value lies between 1 and 10, it will be either 1 point something or 2 point something or 3 point something, maybe even 9 point something. But it can't have anything beyond that, right? So if you consider all possibilities, you'll notice that the value of this exponent will always contain one digit before the decimal and I don't know how many digits after, because I don't know its value, right? But it will definitely has one digit before the decimal, right? Why is that? Because the value of this exponent is greater than 1, right? So it has to be 1 point something or 2 point something or 3 point something or maybe 9 point something, which means decimal will be preceded by one digit. That digit could be 1, 2, 3, 4 all the way till 9, but it will definitely have one digit, right? And then if you take this number and you're multiplying this with 10 to the power 19, what you'll do is you'll move the decimal 19 places to the right, which means what already had contained one digit to the before the decimal will now contain 1 plus 19, 20 digits before the decimal, right? Which means that this number will have 20 digits before the decimal. 10 to the power 19.26 will actually have 20 digits before the decimal. I don't know if it has any digits after the decimal. Now, if you think about it, 2 power 64 can't have any digits after the decimal, right? So it will have all digits before the decimal. How many digits is that? 20. It's a little complicated in terms of explanation, but I hope that you guys understand, right? So what you will do in such questions is take a log and then take an anti-log. And the moment you get an expression which contains 10 to the power something, know that 10 to the power x will have x plus 1 digits. 10 to the power x point something will have x plus 1 digit. So if I got 19.26, I'll say 20 digits. If I got 18.76, I'll say 18 digits. If I got 23.13, I would still say 24 digits. Right? So increment the integer part by 1 and say that's the number of digits. Is that clear, everybody? Do you guys understand this? Try question number 29. Where I'm given the value of log 2, log 3, and we want the value of log 6 to the power 20. Right? Don't forget this part of it. Forget the explanation part of it. At least remember this part. Right? Know where you want to go. Take a log and take an anti-log. That's the process to follow. Right? Let's do that in question number. Which one is this? 29. Log 2 is given 0.30103 and log 3 is given 0.47712, and the question says if n is 6 to the power 20, you want the number of digits here. So taking a log of n will become 20 log 6. That's like 20 into log 6. 6 is 2 into 3. So log 2 plus log 3. Substituting values. 0.30103 plus 0.47712. Adding 3 plus 2 5, 1, 7 plus 1 8, 7, 4 plus 3 7. So 0.77815 into 20. Right? So decimal moves one place and then you multiply 0. 2 5s are 10, 3, 16, 15, 15. And this becomes 15.536. If this is log of n, then n must be, taking an anti-log, n must be 10 to the power 15.563. The moment I get to this point, I know that increment this by 1, end up getting 16. So the given number n will have 16 digits. Great. You guys have understood. Does that make sense? Right? The comparative analysis. The moment I get to 10 to the power something, look at the integer part in the power and increment that by 1. If I have 16 point something, it should be 17. Since I got 15 point something, I should report answer as 16. Does that make sense to you guys? Everybody? Yeah, seems like you guys have. Okay. Some variations. Look at question number 30. Okay, already have two answers that are, I don't agree. Okay, very surprising. What's the class for topic for Thursday? I don't know. I'm thinking that if we finish logs today, we could do a little bit of work on functions. That's what I think. So yeah, Thursday would be functions. Wow. DBAB. So you're picking all choices except for C so far, which is a little disconcerting. Three things which contain logs are said to be in an AP. Yeah, so the starting point is always that when three terms, three numbers are in an arithmetic progression, and you can immediately say that the difference of the first two will equal the difference of the last two. Right? So you can say 3 log of 3 power x minus 2 minus log of 3 should be equal to log of 3 power x plus 4 minus log of 3 power x minus 2. Right? So difference between second minus first will be equal to third minus second. Right? In fact, you don't need to write this because if you remember, you can also write this as 2 times log, 2 times the middle term, second term, 3x minus 2 will be equal to the sum of the first and the last. So log of 3 plus log of 3 power x plus 4. So using the property, power goes inside. This becomes log of 3x minus 2 the whole square, and this becomes, when you add two logs there, radicals get multiplied, 3 into 3 power x plus 4. And just for ease of working, this is, if two logs are equal, their bases are the same, their radicals must also be equal. So 3 power x minus 2 the whole square will be equal to 3 times 3 power x plus 4. In fact, at this stage, let y be equal to 3 power x. So my equation becomes y minus 2 the whole square is equal to 3 times y plus 4. And then I simplify it. So this becomes y square minus 4y minus 3y. So minus 7y plus 4 minus 12 is minus 8. So this becomes y square. So this becomes, you can simplify this, y minus 8 into y plus 1, which means y is either 8 or y is equal to minus 1. Right? So you have two possible values of y. And what was y? 3 raised to the power of x. Right? Can y be negative? Can an exponent take a negative value? No. 3 power x cannot be negative. Which means the only value I'm left with is 3 power x should then be equal to 8. So to calculate this, to calculate the value of x, you take log. So log of 3 power x will be equal to log of 8, which means x log 3 will be equal to log of 8, which means x will be log of 8 upon log of 3. So either log 8 by log 3 or log 8. This is the opposite of change of base, can also be written as log of 8 in the base 3. That's option B. Good. Those of you who managed to figure this out, good. All right. Let's do something which is different. Okay, I want you to try question number 36. Question 36. like a sequence of logs. Yeah, I guess we started about 20-25 minutes late, maybe another till 8:15 or so. I'll do one more question, 36, and then one more question. That's two questions I wanted to discuss. So as long as that takes, I think. So, I mean, the left hand side here has this expression, right? Now, I don't know if you can see the pattern, but the radicands here is the sum of successive odd numbers, right? So every radicand is, so first one odd number, odd natural number. So one, then two consecutive odd natural numbers, three consecutive odd natural numbers, then 4, 5, 6, 7. How many is this? And how many is this? If I write 19 as, this is an AP, right? Odd numbers are an AP. 19 as first term plus n minus 1 times the common difference 2. And you calculate the value of n, you get n as 10. So this is like 10th term. So it contains 10 consecutive odds. Now there's one more trick to remember here, right? So the trick to remember, start sum of first n odd natural numbers is equal to n square. Sum of the first n odd numbers, natural numbers. So 1, 2, 3, 4, 1, 3, 5, 7 till n. Right? Not till n, right? Till the nth number will always be n square, right? Try this out. First two odd numbers, 2 square is 4. First 2 is your 4. First 3 odd numbers, 3 square, 9. Add try checking 5 plus 3 plus 1, 9. Right? So if I think about the last term, this should be first 10 odd numbers, right? So first 10 odd numbers, sum should be 10 square, 100. Right? So this basically, if I use this trick, my question becomes a lot easier. This becomes log 1 plus log 2 square plus log 3 square plus log all the way till log 10 square. And I know that since you are adding multiple logs, this will become log of, I mean, even 1 can be written as 1 square. So 1 square into 2 square into 3 square all the way till 10 square. Right? And obviously the 10 can also come out. So this will become, sorry, the power 2 can be taken common and bring it out. Right? So this becomes 2 times log of 1 into 2 into 3 all the way till 10. Okay, but then what about the right hand side? This one says 5040 square. First of all, the square, in fact, let me not take it out. For this reason, let me put this inside of this code. So how many products will lead me to 105040? So it turns out that 1 into 2 into 3 into 4 into 5. Let me just write this product. And so this is what you have. This is 2 into 3, 6. 6 into 4, 24. 24 into 5, 120. 20 into 6, 12, 6 are 720. 720 into 7 is 5040. So this becomes log of 5040. And then what remains is 8 into 9 into 10. So this becomes into 8 times are 72 into 10, 720 whole square. So if I split this becomes log of 5040. Let me write this like this. No? So this becomes log of 5040 square plus log of 720 square. This is already there in the right hand side, log of 5040 square, which means this should be m log n, right? Which means either m is 1 and n is 720 square. That's not given in the options, m plus n. Or I can write this as 2 log 720. Right? In which case this is m and this is n. So the value of m plus n will be 722, which is indeed there in option C. So my answer becomes option C. 36th correct answer is option C, 722 and 720 whole square. Well, log of that will be 2 log 720. And so m plus n becomes 722. Is that clear, you guys? Right? What have I done? Till here, first I used a trick, write those as 2 square, 3 square, 4 square till 10 square. Bring that in, cumulate it, multiply. And the hint was on the right hand side 5040. So I checked how many of these multiplied either gets to 5040 or close to it. It turns out the first 7 will become 5040. So the last 3, 8, 9 into 10 becomes 720, 720 square. Yeah. I mean, it's only a matter of calculating. Okay. And then I wanted to discuss one more question. Right? This is, but before we discuss this question, right, this last topic deals with inequalities involving logs or exponents. Right? Whenever you're dealing with inequalities, you need to be a little careful, right? Especially when you're dealing with exponents. Why? Right? So let's start with exponents first, right? So if I say a power m is greater than a power n, does that mean that m is greater than n? Right? So if this comes in the exam, 99% of you guys will say yes, m is indeed greater than n. But remember, this is not always true. Right? Why? Let me prove it by way of an example. 0.1 square and 0.1 cube. Which is bigger? What is 0.1 square? 0.01. What is 0.1 cube? 0.001. Obviously 0.1 square is bigger than 0.1 cube. But is the power greater than the power on the right hand side? No, the power is actually smaller. Okay? Opposite of the previous value, right? So basically, the point I'm trying to drive at is that when you're dealing with inequalities, right, it depends on the base. The base, the value of the base is important. You need to account for the base, right? How so? Right? Remember that if the base A is greater than 1, then whether it's a log or it's an exponent, will be an increasing function. What do I mean increasing? Increasing means if you increase the value of x, then the value of y will also increase. Right? On the other hand, if a is not greater than 1, if a lies between 0 and 1, base is never negative. Another thing you should keep in mind, right? When you're dealing with the logarithm or the exponential function, the base can never be negative. Base must always be positive. Right? So base is greater than 1, and in the positive range, all I'm left with is base lying between 0 and 1. If base lies between 0 and 1, then it is a decreasing function. Right? What does this mean? In perspective, what this means is if base is greater than 1, then if I have a power m greater than a power m, then m must be greater than. Or if I have log of x in the base a is greater than log of y in the base a, then x will be greater than y. Right? So the greater logarithm will have the greater radicand. The greater exponent will have the greater power. Right? That's what happens when the base is greater than 1. On the other hand, if base is decreasing, the base size between 0 and 1, then a power m greater than a power n means m is less than n. Or if log of x is greater than log of y, then x is smaller than y. So it's not so intuitively obvious, but if ever you get confused, then look at that example. Right? If a power m is greater than a power n and base lies between 0 and 1, indeed it does, then the greater power, the greater value, the greater exponent will have the smaller power, and the smaller exponent will have the greater power. Right? So it inverses when you are dealing with bases that are between 0 and 1. It's a very important point. Right? And which basically means that there will be a set of questions where you can use this. Look at question number 45. Question number 45. Right? Look at this. It starts with log of 3x minus 1 divided by 2 minus x in the base 2 less than 1. Right? So you have an inequality. The moment I look at this inequality, I should think, okay, a logarithm must be less than 1. Can I write 1 as another log? Sure. I can write, and I want the base to be the same. So what 2 power 1 makes? 2. So I can write 1 as log 2. 2 raised to the power 1 makes 2. So I can write this as, replace 1 as log 2 in the base of 2. So now look at this. I have one log greater than the other log when the base is greater than 1. So when the base is greater than 1, the log that is greater will have a radicand which is greater. Right? So immediately in this question, I can directly use this property and start is immediately saying then 2x minus 5, then the radicand 3x minus 1 by 2 minus x must indeed be smaller than 2 because the base is greater than 1. But in this question is especially tricky because there is one more constraint that we will need to use. Right? Since the radicand contains x, there is one more important property. Just like you're saying that an exponent is always positive, similarly, in log of x, x must always be positive. So whenever you have a logarithm, the logarithm will exist only if its radicand is positive. So besides saying that the radicand is less than 2, you must also say that the radicand is greater than 0. And that's the starting point for this question, right? Because it's this log is less than this log, its radicand must not just be smaller than this radicand, but it should also be positive. It should also be greater than 0, right? So this becomes two inequalities, right? So I'll solve both of them separately. So we say 3x minus 1 by 2 minus x is less than 0, and 3x minus 1 by 2 minus x is less minus 2. I hope that you guys are following, and then you can solve it, right? So how do I solve it? The first inequality, I'll simply plot the critical points. The critical points, numerator becomes 0 when x is 1 by 3. Denominator becomes 0 when x is 2. Right? And the moment I have two critical points, I'll know there are three distinct regions. Let me substitute any value from one of the three regions. Right? I like to substitute origin. I like to substitute x equal to 0. So first of all, where is x equal to 0? Less than 1 by 3. So x equal to 0 is in the leftmost region. But when I put x equal to 0, numerator becomes minus 1. Numerator is minus 1 and denominator is 2. Yeah, so the value of 0, value at x equal to 0 is negative. So value is negative, which means the next region the value will be positive, and the region after that the value will again be negative. This is the rule of alternating signs. So the moment I get minus plus minus, you go back to the inequality and you say, okay, what value were we evaluating greater than 0? So we want the greater than 0 part. Where is greater than 0? Positive. Positive is this region. So immediately I'll say solution here will be x lies in this region, which means x lies between 1 by 3 and 2. Remember, it can't be equal to 1 by 3 or it can't be equal to 2, right? Because if it is equal to 1 by 3, this numerator will become 0. And a radicand can never be equal to 0. It has to be greater than 0. So x can neither be equal to 1 by 3 nor it can be equal to 2. It must lie strictly between these two values. Similarly, to solve this inequality, I'll bring the 2 to the left hand side and take an LCM. This will become minus 4 minus 2x plus 2x upon 2 minus x is less than 0, which means I get x minus 5 divided by 5x minus 5. So this will be 5 times x minus 1 by 2 minus x is less than 0. Again, plotting the number line, critical points 1 and 2. Again, calculating f of 0. What is f of 0? Minus 1 minus 5 divided by 2. So f of 0 is minus 5 by 2, which is negative. And 0 is to the left of 1. So here it will be negative, then positive, and then it will become negative. But this time I want the less than 0 sign, which means I want negative. Where is it negative? X is either less than 1 or x is greater than 2. So less than 1 or greater than 2. So to combine these two because, this is not all, this is an AND. Both these conditions must be true. So x must be, whenever it's two conditions and you want to find the common region, you can put this on a number line. First condition is, I have the critical points 1 by 3 and 2, and it says 1 by 3 to 2, open, right, 1 by 3. So it can be greater than 1 by 3, less than 2, and between them, but it's all points except the values 1 by 3 and 2. Similarly, second region x less than 1. x1 is over here, right? It's somewhere over here. So this is 1, then x is less than 1 or x is greater than 2. Right? And you want both conditions to be met because, so which point lies in both the solution sides? You can see this region. You can see this is the only region where there is an overlap. Otherwise, here the second condition is met, not the first. Here, first condition met, not the second. And here, second is met, not the first. Right? So, the solution will be x lies between 1 by 3 and 1. That's your answer. So, answer is option A. Question number 45, the answer is option A. A. X lies between 1 by 3 and 1. Yeah. This one is obviously one of the harder question types from inequalities, right? So if I recap, you can have basic inequality problems where all you need to do is calculate the value by maybe taking an antilog. Second, you'll have questions involving the properties of logarithms, whether what happens when they're added, subtracted, or multiplied. And then you'll have variations involving logarithms in either sequences or in progressions or in inequalities. Right? And so you need to be comfortable with doing all that. All right, I hope that this session made you guys a little more comfortable with the topic of logarithms. In case some of you are attending this for the first time, make sure that you download the exercise. Well, that's all I have for you guys today. Any questions, any doubts? Do let me know. Do post it in the comments here. I'll try and address it before the next class. Okay. All right, thank you guys, and see you on Thursday.